Hi guys, welcome back to another video. Today I'm going to show you how to find the eigenvalues and eigenvectors of 2 by 2 matrices. So let's start with the definition. So the definition, a non-zero vector v in R square is called an eigenvector of 2 by 2 matrix A if and only if AV equal lambda v. So the scalar lambda is called eigenvalue, and lambda is an eigenvalue of 2 by 2 matrix A if and only if determinant of A minus lambda I2 equals 0. So I2 is the identity matrix, and we're gonna apply this definition in a concrete example just in a bit. So let's finish with the definition here. So the determinant of A minus lambda I2 is called the characteristic equation. So let's apply this definition and see how we can find the eigenvalues and eigenvectors of the given matrix A equal 1, 2, 4, 3. So let's find the eigenvalues first. So we start with the determinant. Determinant doesn't look like the determinant of A minus lambda I2. So that's the determinant of 1, 2, 4, 3 minus lambda I2 is 1, 0, 0, 1, which is going to be the determinant here. So 1, 2, 4, 3, nothing changed here, minus, so multiplying by the scalar, it's going to be lambda and the diagonals, 0 and lambda here. Now subtracting two matrices from each other, it's going to be 1 minus lambda here, 2 minus 0 is 2, 4 minus 0 is 4, and 3 minus lambda. And find the determinant of this. It's going to be 1 minus lambda times 3 minus lambda minus 4 times 2. So this is the characteristic equation. So let's solve it. So 1 minus lambda times 3 minus lambda minus 8 equals 0. So if you distribute this, you get lambda square minus 4 lambda minus 5 equals 0, and these can be factored nicely. Lambda minus 5 and lambda plus 1. So the eigenvalues of this matrix, eigenvalues are lambda 1 equals -1 and lambda 2 equals +5. So now let's apply the definition of eigenvectors. and find the corresponding eigenvectors. So let's do V1 is the corresponding eigenvector to the eigenvalue lambda 1 equals -1. So the definition is going to be a V1 equals lambda 1 V1, and a it's 1 2 4 3. V1 we don't know, that's what we're looking for, so let's see V1 and V2. That's the entries of the vector V1 equals lambda 1, it's -1, times V1 and V2. And now let's solve for V1 and V2. So multiplying matrices or matrix by a vector. So it's going to be 1 times V1, it's V1, plus 2 times V2 is 2V2, equals multiplying a scalar, -1 by a vector, so negative V1 here. Same thing for the second row, so 4V1 plus 3V2 equals -V2. So I have a system of equation here with 2 variables and 2 equations. So let's use the first equation and solve for V1 or V2 in terms of the other. So here, first equation. So if I subtract V1 from both sides, I get 2V2 equals -2V1. And that's leave me with V2 is the same thing as -V1. So now if I replace V2 with -V1 in the second equation here, so 4V1 plus 3V2, which is the same thing as -3V1, equals minus V2 is the same thing as positive V1. So solving here, so here I have 4V1 minus 3V1, that's give me V1 equals V1, and that's mean V1 can be any constant. So V1 can be any constant k, where k is a real number. So if V1 is k, V2 is -k. So the corresponding eigenvector of lambda 1 equals -1, so it can be V1 as k and -1, 1 -1, or -1 1, doesn't matter. So this is the eigenvectors. So k is a constant and it's a real number, so there is infinity many vectors, but one example can be 1 and -1. So let's find out the eigenvectors V2 that corresponding to lambda 2 equals 5. Same way, so we do here a V2 equals lambda 2 v2. Same thing here. The matrix 1 2 4 3, and v2, let's see, we do u1 and u2 equals 5 u1 u2. So same thing, multiplying matrix by a vector. So I get u1 plus 2u2 equals 5u1. And here we have 4u1 plus 3u2 equals 5u2. Same thing, a system of equation with two variables and two equations. So let's solve for one variable here in the first equation and substitute it in the next equation. So if I subtract u1 from both sides, I get 2u2 equals 4u1. 4u1, yeah, so 4u1. So that's mean u2 equals 4 over 2, which is 2u1. So now substitute 2u1 for u2 in the second equation. So 4u1 plus 3u2, that's mean plus 6u1 equals, and 5u2, that's mean 10u1. So combine like term here, I have 10u1 equals 10u1. So that leaves me with u1 must be 1. And if u1 is 1, u2 is 2. So u1 is 1 and u2 is 2. So now the eigenvector that's corresponding to lambda 2 is v2 equals k 1 2, where k is a real number. So those are the two eigenvectors that corresponding to the lambda 1 and lambda 2. So it's worth mentioning that the determinant of A minus lambda I2 equals lambda square minus 3 of A times lambda plus the determinant of A. So where the 3 is the sum of the diagonal entries. So in the last example, we have the determinant. So the determinant of A minus lambda I2. We find that after we simplify everything, it was like lambda square minus 4 lambda minus 5. And the matrix was 1 2 4 3. So the 3's is the sum of the diagonal entries, so it's 1 plus 3, so that's the that's the trees. 1 plus 3, which is 4, so that's negative, so that's the negative trees A times lambda. That's what we get, negative 4 times lambda. And the determinant of A is 1 type of A is 1 times 3 minus 4 times 2, which is 3 minus 8, which is negative 5. And that's the trees, that's the determinant of A. So that's how this formula comes from. And the product of the eigenvalues is equal to the determinant of A. So we find, in last example, we find lambda 1 equal negative 1 and lambda 2 equals 5. And we know the determinant of A is negative 5. So the determinant of A is negative 5. And that's the same thing as lambda 1 times lambda 2. And also the trace is the sum of the eigenvalues. So we know the trace is 4. Trace of A is 4. And that's the same thing as lambda 1 plus lambda 2, which we find negative 1 plus 5, that's give me a positive 4. And that's also explanation to this fact. So I hope you enjoy watching this video. I will continue next time. Thanks for watching.